Math 287, Cuesta College. I'm Joe Vasta, and we're going to cover 10.5, the first shifting theorem when it comes to Laplace transforms. So we have a function called f of t. You take its Laplace transform. It's a linear transformation that takes this vector to something called f of s. So we've already encountered the Laplace transform of these functions here, and we solved some differential equations. So what we're going to do today is we're going to use something called the first shifting theorem, which I did not write all the way down. We are going to derive this on PowerPoint. Okay, so what we're going to do is we are going to take the Laplace transform of g of t. Okay, so this is kind of weird here. I mean, what is this all about? We are going to prove the first shifting theorem, so let's go ahead and do it. Our next step is we make a substitution. So this is capital G of s equals this. So capital G of s minus a, everywhere there's an s up here, we replace it with s minus a, and there's only one occurrence of an s, and it's right above that red circle. So we replace that s with an s minus a. Okay, so the next step is we're going to break up that e to the power using just rules of exponents. Okay, so I break it up into that, and then we look at this, and we are going to group these two guys together. So when that happens, I have integral from 0 to infinity e to the negative st times this function right here, which is really the Laplace transform of e to the at g of t. So this gives us our first shifting theorem, and it's weird, you know, I mean, seeing the proof of this, it's like, what just happened? We just proved this right here, that if you have a function e to the at times g of t, the Laplace transform is capital G of s minus a. And it seems, you know, right now it might seem a little abstract. We are going to do some examples when we go back to the paper. So we have just proved the first shifting theorem on the PowerPoint. And there it is right there. E to the at g of t gets transformed to capital G of s minus a. Looks very abstract, so what we're going to do is we're going to do some examples. We're going to find the Laplace transform of things that we wouldn't be able to find the transform of just using these rules up here. Okay, find the Laplace transform of f of t equals t to the fourth e to the 7t. So what I'm going to do for this particular problem is I'm going to do this problem the textbook method. Okay, and then after I do, I'll do the textbook method over here in purple, and then I'll show you the way that I do this. Okay, so the textbook method. Okay, the textbook method says that we want to see that this fits the mold. We know that it's a first shifting theorem because we have an e to the at. So with the textbook method, you would identify what g of t is. G of t is the other part, which is that t to the fourth. So we have that right there. And there is nothing wrong with the textbook method. So now what I need to do is I need to find out what capital G is. I'm going to take the Laplace transform of that. So this is g of s. Now these Laplace transforms you should be memorizing just like you would memorize how to take the derivative of that. The Laplace transform of t to the fourth is 4 factorial over s to the fifth. So that's really 24 over s to the fifth. Okay, so now what I'm doing is I'm kind of just using this as my roadmap here. I'm going to now go g of s minus a. So this is going to be g of s minus 7. And that gives me 24
over s minus 7 to the 5th. So we have just found the Laplace transform of f of t. It happens to be 24 all over s minus 7 to the 5th power. And so there's the textbook method, and that method will work all the time. Now, I'm going to go ahead and show you the way that I would do the problem. Okay, so if I was doing the first shifting theorem, let's go ahead and circle this A in red as well. I would see the e to the 7t and realize that I was going to do the first shifting theorem. So what I would do now is I would go ahead and write the answer almost. So this is f of s equals. I'm going to temporarily ignore that e to the 7t. I'm actually doing the textbook method, but being more efficient about it. So temporarily ignore that and say, what is the Laplace transform of t to the 4th? Well, it would be 24 over s to the 5th. Now, everywhere I put an s, I'm going to put parenthesis s with some room there to the 5th. So that is what the Laplace transform of t to the 4th is. And then, because I'm looking at the shifting theorem, I'm going to account for the shift and put minus 7 right there. And look, it's the same answer. I pretty much did the same thing, except we're being a little more clever about it. So in the next few problems, I'm just going to use my method. At any time, you can write down the textbook method and do it that way. So problem number 2, find the Laplace transform. And on each of these pages, I put the first shifting theorem up in the top right corner. If this were a face-to-face class, I would actually give you the first shifting theorem on the exam. But I wouldn't give you the other Laplace transforms if this were face-to-face. So let's go ahead and do this the same method I did problem number 1. I see there is a shift at e to the negative 2t. So there. So I'll circle these in red here. So what I'm going to do is, maybe this is what you should do, is pause the video and write down the answer. Okay, so what I'm going to do is I'm going to ignore that red thing temporarily and ask myself, do I know the Laplace transform of 5 sine 3t? Well, yeah, we do. So this is f of s equals, well, 5, we can put that right there, sine 3t. The Laplace transform of sine 3t, it's sine bt, and that's the one where the b is on the top. So this is going to be b over s squared plus b squared. So this is going to be 3 over s squared. Now s squared, you need parentheses there, so s squared plus 3 squared. Okay, so now what I'm going to do is I'm looking at this the whole time, and I'm going to account for the shift. So, you know, a is negative 2 here, so I'm going to go s minus a, or s minus a negative 2. So I'm actually going to put s plus 2. Of course, I want to clean up my answer here. So, you know, I want to write f of s is, see, on the top we have 15. And on the bottom we have s plus 2 squared plus 9. Now you might say, should we multiply out the bottom? Nah, this is good enough. So we'll box that, and that is how you take the Laplace transform using the first shifting theorem. Let's go ahead and do problem number 3. Once again, I would ask that maybe you pause the video and try to find the Laplace transform on your own. Okay, so I have that right there, and that right there. And it looks like I'm going to break this up into 2 problems. So here, well, you know what, actually, and we'll talk about this at the bottom of this page. We can actually find the Laplace transform of e to the negative t. that is on our list. We have an e to the at on our list. So this is really going to be 1 over s minus a negative 1 or s plus 1. So that gives me the Laplace transform of e to the negative t. This one's going to be something that we can't do straightforward. We have to use the first shifting theorem. So let me circle this part in red. I'm going to temporarily ignore that and say, do I know how to find the Laplace transform of the cosine 6t? And the answer is yes. That's the one with the s on the top. So this is going to be minus because of the minus. We put s on the top within parentheses. S over s squared plus 6 squared. So we'll just say plus 36. So we can do that in our heads. And then we'll account for the shift. Well, the shift, we have a is 4, so we're going to go s minus. Everywhere there's an s, we put an s minus 4. And there's not much more we can do here. I know some of you would say, hey, put those fractions together. No, I'm not going to do that. This is, and it wouldn't matter if you were saying put those fractions together. This is a video, so what good is that? You can say it all you want. I'm going to keep my answer like that. So that completes problem number 3, finding the Laplace transform of functions using the first shifting theorem. Now I want to point out something. Let's just say f of t equals just the function e to the negative t, like it was there. Well, we learned that we can just use the one on the list that says e to the at gets transformed to 1 over s minus a. But we could also realize, this is killing an ant with a cannon. It's pretty messy, but it still gets the job done. You can realize that that right there is a shift, and the function that's sitting next to it is 1. Or t to the 0 if you'd like. And so the Laplace transform of this is really, well, the Laplace transform of 1, which is t to the 0, 0 factorial over s to the 1, which is 1 over s. 1 over s. And then we account for the shift, which we go plus 1. So we'll call this problem 3.5, just to annoy all those perfectionists out there. You're like, hey, what about 4? No, I don't want problem 4. I wasn't planning on doing 4 of them. And there's the answer. We really don't want to do the problem this way. We could. See, this is the same function. We just want to say, oh, I know how to deal with e to the at. But when you were doing e to the at in the earlier sections, you were actually doing the first shifting theorem without even knowing it. Just think of all the things you do in a math class without knowing that you're doing that. So that's something that's pretty scary. Like when you do integration and differentiation in calculus, those were really linear transformations, but you didn't know anything about linear transformations when you walked into your first calculus class. But when you were doing integrals and derivatives, that's exactly what you were doing. Let's go ahead and change the problem around. Now we're going to go backwards. We're going to give you some s expression and ask you to find the inverse Laplace transform. Okay, so find the inverse Laplace transform of that function. And I'll get the shadow effect there. Okay, so wow, we've got to go the other way now. Let me go ahead and circle the things in red that I've been circling in red. And I'm going to do the same thing that I did before. I'm going to show you the textbook method over on the right in purple. So the textbook method happens to be, looks like I have a shift here. I have a plus 2. So I'm going to go ahead and label g of s minus a, but it's actually going to be g of s plus 2. So that's where I first start off. I take this whole thing and label it as a shift on capital G. So g of s plus 2 is just the thing you see on the right hand side. So this is 1 over s plus 2 to the 4th. Okay, so now what I'm going to do is I need to figure out what just plain g of s is. To find out what just plain g of s is, I mean, one way you can replace all the s's in this equation with an s minus 2. And some of you already knew what g of s is. This is going to be, the other way is just seeing what it's going to be. 1 over s to the 4th. Of course, it's easier to go from here to here and go, oh yeah, I can plug in s plus 2 everywhere. And so there is g of s. I need g of s so I can figure out what g of t is going to be. G of t, I am taking the inverse Laplace transform of this. Now to take the inverse Laplace transform, I need something on the top. So, you know, you can look at your Laplace transform of t to the n. You need not a 4 factorial on the top, but a 3 factorial. 3 factorial. Of course, 3 factorial is really what? It's 6. So I'm going to put a 1 over 6 on the outside to balance the books. Okay, so now we're ready to energize, and let's see what planet we take this thing to. We're taking it back to the land of t. I have the 1/6, and this is now going to become t to the 3rd. Okay, so I'm looking at my roadmap up here. Okay, so what I need now to get the whole answer, to get f of t, little f of t, is I need to go e to the at times g of t. And so little f of t is e to the at. Oh, and what is a in this example? A is -2. So e to the -2t. And then we have t cubed, and I'll write it like this, over 6. And so that is how I find the inverse Laplace transform, using the first shifting theorem, doing it like normal textbooks would do this. Now, let's go ahead and do it Joe's way. This is the way I like to do it because, I mean, yeah, that was cute, but it takes a long time. So I'm going to do kind of what I did when I did it my way, going from the land of t to the land of s. Now I'm going from the land of s to the land of t using an inverse transform. I'm going to temporarily ignore that plus 2 there. Okay, so I can see that a equals, what does a equal? A equals -2. Okay, so I know I'm going to ignore that and say, can I find the Laplace transform of 1 over s to the 4th? And that's what f of t is going to be. Now I'm not going to play that whole game where I put the 3 factorial on the top and do that. Okay, so we kind of already know what's going to happen. The Laplace transform of 1 over s to the 4th happens to be t cubed over 3. Okay, so at the very end, and I'm using this as a roadmap, I'm going to multiply my result by e to the at, which is e to the -2t. And that's how we can take 20 steps and make it 1 step. And yes, that was an exaggeration. That is not 20 steps. That looks more like 18 steps over here. Well, anyway, we went 1 step. So do it how you want to do it. Okay, so this is how the beginners do it, and this is how the professionals do it. So, you know, people actually join competitions where they're taking inverse Laplace transforms and they're facing off against their opponents, and it's really fun to see. But we can't do that because everybody's social distancing. So when this whole pandemic is over, I mean, I plan to go to the Laplace transform games and just cheer my favorite team. So there it is. So there it isn't. that right there should be a 3 factorial. Okay, so my final answer should be e to the negative 2t, I'll put that first, t cubed all over 6, and there it is. So let's go to the next problem. Find the inverse Laplace transform, problem 2. Okay. Now, if you want, you can pause the video, though this one's going to be quite traumatic. You might not want to pause the video because you might say, whoa, how do you do this? So this is what we're going to tackle. Does the bottom of this fraction factor over the rational numbers? And the answer is no. Factors of 13 that add up to 6, you're never going to find them. So, if it did factor, let me just point that out here, because some of you might just be looking at the PDF and say, what did he say about that? So, if the bottom, and I'm a math teacher, I should be saying denominator, but I try to go minimal. I try to minimize my syllables. If the bottom factors over the rationals, then do partial fraction decomposition. So we've done that in an earlier lecture. This does not factor. So you might say, we're done then. No, it's time to get traumatized. Okay, so here it goes. F of s equals s plus 5. Now hopefully you're at the level where this does not cause a panic attack, but you never know. There's still some people in this class who are going to run away from their computers when they see what I'm going to do, and it's a very simple thing. I'm not saying what I'm going to do is simple, but watch this. I have s squared minus 6s, and then I leave a space and then put the plus 13. So some people are like, oh, shift. I did say shift. They're like, wow, what is happening here? You guys know what I'm going to do on the bottom. And if you don't, shame on you. No, if you don't, well, I'll just tell you, I'm going to complete the square on the bottom. Was it an obvious thing? No. So you might be, well, how did you know, Joe, that you had to do that? Because I had to learn how to do these things. Okay, so it's not like I came up with this. So how do I complete the square on the bottom? I take the negative 6. I chop it in half. There has to be a 1 in front of that s squared. If there's not, then you have to factor it out. But we have a 1 there. Take negative 6, chop it in half, and square it. That's the little recipe that gives us the magic number here. What is the magic number? The magic number is 9. Please don't tell other instructors, especially professors at the university, that I was calling this the magic number. But it is. Okay, so watch this. Plus 9. There really is no magic. This is all mathematical that this will work. And then what am I going to put over here? And lots of people, like in lower classes, they go, put plus 9 there. And yeah, you're not doing my taxes. We're going to put minus 9. Okay, so that kind of balances the books in the denominator. So what happens here, that right there is a perfect square trinomial. So let's go ahead and write that up. This is f of s equals s plus 5 all over s minus 3 squared. So that's what that becomes. And it's this number right here, negative 3, is always the number you see in there. And then I'm going to go 13 minus 9, that is 4. So at this point, you're like, well, okay, so we completed the square, and we ended up getting this. A lot of you are going, well, look, that reminds me of, like, perhaps the sine and the cosine. Okay, so I'll kind of move this like this. See, there's the cosine and has an s on the top. Well, maybe that's what we're going to use, the cosine. And then the sine just has a b on the top, just has a number. Well, here's the deal. So some of you are like, well, let's do the shifting theorem. But the problem is, on this s, it is s minus 3. And so if you have more than one occurrence of s and you want to do this theorem here, they both have to say s minus 3s. And so we do not have that. So what are we going to do? Well, let's go ahead and write this again. So on the bottom, I have s minus 3 squared plus 4. On the top, I'm going to go ahead and put the 5 over here. Now, some of you are like, oh, he's going to complete the square on the top, but there is no square on the top. What I'm going to do is something maybe a little simpler. What do I want on the top? I want a minus 3. There's probably more than one way of getting my result that I'm going to get. So I have a minus 3 there, so I should put a plus 3 there. So what does that give me? So I'm running out of paper here, and I really do want to finish this up on this piece of paper. I end up getting s minus 3 plus 8. I am now going to split the fraction and keep the same denominator for both of them. So the first part of the first fraction is going to say s minus 3 all over s minus 3 squared plus 4. And then this one's going to say plus 8 over s minus 3 squared plus 4. So I haven't even done the inverse transform. I'm getting it ready so we can do the inverse transform. Now, look what I have. Everywhere there's an s in this whole expression, it says s minus 3. So let's look up here. I'm going to ignore this minus 3 temporarily, and hopefully we can write out our answer on this. So this is f of t equals, I'll leave a little space there. What is the inverse transform of s over s squared plus 4, or s over s squared plus 2 squared? Well, that would be the cosine of 2t. Okay, now I'm going to do the inverse transform of 8 over s squared plus 4. Well, this one is going to be the sine, and the b squared, you know, we have b squared right here, so b is 2. You need a 2 on the top. And so this 8 is really 2, and I'll leave that there, times 4, which I'll pull out front. This guy is energized. We're going to go ahead and take the inverse transform. That 2 is going to disappear. This whole thing's going to become plus 4 sine 2t. Okay, so that's doing the inverse transform, ignoring the minus 3's on each s. And now I have to account for the shift. And how do I do that? And you could look back at the other problem. This is exactly kind of what I did. I'm going to go ahead and say this is going to be e to the, well, in this case, a is 3, so this is e to the 3t. There's my answer. Barely had enough room, but there it is. So here's the cool part, is you could actually cover up all the work that you've done, take this answer and do the Laplace transform. And you should be able to get that for your answer. And that will be the case. So that's maybe, you know, like if you're studying for the exam and you're like, oh, maybe I want to do one that I didn't already do, you can do that. Take one of your answers and do the opposite direction. So some of your problems in the homework will require a partial fraction decomposition. And that's when you are going from the land of s back to the land of t. So there's the answer. Let's go ahead and do an equation now. So we've done a few Laplace transforms, we've done a few inverse transforms, and now let's see how this is going to help us solve this differential equation. So, you know, maybe I think there are some people in here who could turn off the video or pause it and see if you can get the results. That would probably be the best for people who can, you know, we've already solved the differential equation. The only new thing we're doing, and we've already practiced it, is do the first shifting theorem. And we'll be doing it probably both ways within this problem. Okay, so let's go ahead, and the first thing I'm going to do is I'm going to Laplace both sides of this equation. That's cool. Laplace was a mathematician, and just to use his name like that, like I'm going to Laplace both sides, that's kind of cool. I mean, to have your name used like that, or maybe not. Maybe that sounds bad. So what I'm going to do is I'll write things out here. Laplace transform of y double prime minus 6 times the Laplace transform of y prime plus 9 times the Laplace transform of y. So that's the left-hand side of the equation. And then this equals the Laplace transform of t squared times e to the 3t power. Okay, so now we got to remember these formulas. The Laplace transform of y double prime, that's the one that had the s squared. So this is s squared L of y minus s y of 0 minus y prime of 0. So this guy right here became these three terms right there. Okay, minus 6 times the Laplace transform of y, so this is minus 6, y prime. So this is minus 6, and then this is the one that was catchy. This is sly minus yo. So y, L of y prime is sly minus yo. Okay, and then we have plus 9 times the Laplace transform of y. So for all you firstborns out there, I'll go ahead and do it. Okay, so this part right here became that part. And we need another color here. Looking for green maybe. Oh wait, I just used green. Wow, this is great. Okay, I'm looking for blue. Yeah, I wasn't very good at colors in preschool. I think I failed the first unit. You know, what color is that? And I'm like, red. So, getting better. Okay, so now we have the Laplace transform of this junk right here. Well, this junk right here is something that we're going to use the first shifting theorem. Here's the first shifting theorem. I'm going to ignore this e to the 3t temporarily and say, well, what is the Laplace transform of t squared? Laplace transform of t squared happens to be 2 factorial over s to the third. So that's what it is. It's 2 factorial all over. Now remember, you're kind of doing the first shifting theorem, so everywhere there's an s, you put parentheses, s to the third power. Okay, now I'm going to account for the shift. Inside this parenthesis, I'm going to put a minus 3. Okay, so that right-hand side becomes this. After I do the Laplace transform, we use the first shifting theorem. Let's go ahead and plug our initial values in as we do this problem. And I'm also going to replace my L of y's with w's, with some letters, so I can just write the w's easier. S squared w minus s times y of 0. So minus, what is this, minus 2s. And then I have minus y prime of 0, so minus 6. And then this is going to be minus 6 times s w, I'm inside the brackets now, minus yo, minus y of 0, minus 2. And then we have plus 9w. This equals 2 over s minus 3 quantity squared. Okay, so I'm going to do a little algebra on the left-hand side. Don't want to skip too many steps, I suppose. So this is minus 6SW when I distribute the negative 6 plus 12 plus 9W equals the right-hand side. That's me being lazy. I'm going to group all my W's together, so I have S squared W minus 6SW plus 9W. And then what do I have here? I have minus 2S, and then this is plus 6. And this equals the right-hand side. And now I'm going to keep my W's on the left-hand side, and I'm going to factor out one of them. Well, that's the only thing I can factor out. So this is S squared minus 6S plus 9. Now, well, we're moving on here, but before we move on, let's point out that that right there, if you put R's in there, that would actually be the characteristic polynomial of this differential equation if that was a 0, or the associated homogeneous differential equation. I'm going to bring these two terms to the right-hand side, and then we'll play that game, should we make them all into one fraction or not. So let's go ahead and do that. I'll put them on the right-hand side. So this is 2 over S minus 3 squared. And then this is, what? This is plus 2S minus 6. Okay, so we're going to have to move on to another piece of paper here to do this. On the left-hand side, this thing is going to factor, so this is W. We have S minus 3 squared, so that actually factors into S minus 3 times S minus 3. This equals 2 over S minus 3 squared. And, oh, okay, so here's the other thing. This is me going right-hand side each time. I went ahead and I miscopied it, and I was even saying the wrong thing. That's a cube there. So shame on me for being lazy. See, what this is just an example of what laziness can do. It could create mistakes. Okay, so no one will even know when they're looking at that. They'll say, "Oh wow, he draws his threes crazy, but still looks good." Okay, so let's move over here and say plus 2S minus 6. So the question is, should we combine those into one fraction? Well, I'm going to divide by an S minus 3 squared, so this is going to give me 2 over S minus 3 to the 5th, which I can then do for shifting to get back home. So that guy can be inverse Laplaced pretty quickly without any partial fraction decomposition. But take a look at this right here. What can I factor out of here? I can factor a 2 out, and I'll have an S minus 3, which will cancel on one of those. So I'll show you what I mean here. Now, if that didn't happen, I might put them together. I still might keep them separate, especially if I can do one of them without partial fraction decomposition. And it looks like I might be able to do both of them. So there's a normal 3 there. I have plus 2, and then we have S minus 3. Okay, let's continue. I'm trying to solve for W, so I end up getting W equals 2 over S minus 3 to the 5th. And then this is going to be plus 2 over S minus 3. Okay, because there's one of them right there. Yeah, I definitely can inverse transform that, and I can inverse transform that using the first shifting theorem. Let me go ahead and write another step right here before I do that. L, and I'll write this in black, L of Y, because that's what W is. And I'm just going to write the right-hand side. I'll just keep it the way it is. Okay, now we are going to do the first shifting theorem. Let me just remind you what it is. Put it up right here. E to the AT, G of t gets transformed to G, capital G of S minus A. Okay, so there it is. Put it in the top right corner of the paper. So let's continue here. I'm going to inverse transform both sides of the equation. So that's L inverse. So the inverse Laplace transform of the Laplace transform of y is y. Okay, the inverse transform of this, I see there's a shift here, so I'm going to circle that in red. I'm going to ignore that minus 3 temporarily. So I have 2 over s to the 5th. Now 2 over s to the 5th, I need not a 5 factorial on top, but a 4 factorial. So what is 4 factorial? Isn't 4 factorial 24? So I need an extra, whoops, I need an extra 12 up there. Okay, so 12 times 2 gives me 24, which is the 4 factorial. But I have to balance the books by putting a 1/12 out front. Okay, so now it's time to energize. That 24, all that's going to go away. It's going to become t to the 4th for that inverse transform. So this is really t to the 4th all over 12. And now we're going to not forget the shift. It's going to be multiplied by e to the 3t. And the last one, the inverse transform of 2 over s minus 3 is going to be 2e to the 3t. So wow, we finished this differential equation. We finished solving it. We ended up getting the answer. And I'll tell you one thing right now. I did this problem other ways. Okay, and I can tell you, and you might not believe me, so maybe you can do this the other ways as well. I did this problem using undetermined coefficients. So it's doable, but it was a lot more work. And this is not all the work. I'm covering up some of the work that we did, but it was more work than we did. I also did this problem using variation of parameters, and it was even more work than the undetermined coefficients, which was more work than what we did. So this is sweet. We still haven't seen how sweet the first shifting theorem can be, because so far we've only solved differential equations that we already knew how to solve. And sure, on this one it was a little faster than using other methods, but the sweet part of Laplace transform is when the right-hand side happens to be piecewise continuous or something crazy. I mean, there's something called the Dirac delta function. In the real world, weird things can happen for the driving function. And the Laplace transform does a really good job with some of those weird functions. So this completes 10.5. Keep doing your homework. We are almost done with this semester. And have a good day.